there we go. Hello. Hello. Everybody should be
there.
on here. So let's see. Let's make this and let's also put in the chat here. Hello to everybody. Thanks for joining in today. Let's do a quick check. Scott and Nebula, can you both hear us?
Hey, can you hear me? I can hear you.
Yes.
Yeah.
All right.
Perfect.
Oh man, this is fancy. Look at us now.
Yeah, that's definitely
very
fancy.
professional. Yeah.
We're trying to get professional here. That's amazing.
That's good.
It is lovely to have all you guys watching and joining in here today. Welcome back to the streaming session. So this is the HB sniffing session that we are introduced last year with Scott, Jonathan, and myself. And we will definitely continue on this. We will definitely do more videos about this, more streams. We will try to educate as much as we can. And we are trying to do fancy stuff. There's a hello from Alexander, hello back. And yeah, I think Scott, Jonathan, and we are commonly used to the people, but we do have a special guest here. That's NebulaMiner. Would you mind to introduce yourself today?
Yeah, for sure. So hello. I'm just another nerd on internet who spent too many hours looking at this UART and SPI and I2C bus between the control board and the hashboard. So I joined basically. I stumbled upon the Bytex project when it was on the Econ Talk forum, and then I contacted Scott and told him that I wanted to join my effort and to spend hours beside him to make this project a big success. By myself, already 10 years ago, in 2013, I did develop a small home miner at the time, at the first generation of ASICs going out. And of course, it was not a success because everybody wanted to do industrial miner with a high hash rate and a big efficiency. So the fact that people should consider doing home mining for decentralization was not the main concern at that time. But then when I saw the Bytex project, I said, oh, maybe it's reborn of my old idea. So I want to join and I want to contribute. I want to make it better. So basically, I contacted Scott 1.5 years now ago, and then I made the first Bytex Max schematic review. I tried to help also on the software side, and but my main contribution was on reverse engineering the Bitmain original firmware to understand the protocol and to document the protocol. So to write the documentation, basically a small datasheet of the register and how to communicate with them. Why are they for? What is the field? Each bit, what is it for? So there is still a lot of darkness in this documentation because nothing is 100% understood. But we did enough progress to have the firmware of BitX able to hash actual meaningful hashing. So we did that at the time, and then we moved back to the to try to understand more the new chip because Bitmain continue to provide new chip. So basically, the protocol is 80% the same, but there is new register, new feature, new skills, just like the version rolling that you were talking last time. And so we have to understand the new register and to update the documentation. And so this stream you are doing is very important for me because it was a huge part of my next year contribution. I spent countless of hours on that, and me seeing you doing that now, I'm very enjoyed, and I want to share my knowledge. I want to spread what I know, so everybody can continue on the path I started last year. And of course, maybe I will join again and do some debugging with you guys.
I wanted to follow up on that real quick. So as Nebula mentioned, he was one of the first people to message me on the BitX project when it was first getting started, and he was just like, "Oh my gosh, I got all these ideas," and he provided, like you said, the schematic review of what was new at the time, which was the BitX Max based on the 1397. ASIC. And yeah, it was super cool. Nebula just showed up and was like, hey, yeah, I'm good at this. Like, let's do it. And he just jumped right in and started helping a ton. So I would say he is one of the original BitAxe hackers, and one of the, as far as I'm concerned, one of the original hackers of the Bitmain ASICs. So it's pretty cool to have him a part of this live stream, which has become sort of a pretty cool, Bitcoin mining ASIC hacking stream, where we just talk about, how to dive into these things and how to get it working. And so Nebula knows a ton about that, and it is awesome to have him here.
Thank you, Scott.
Yeah, definitely had fun having you here, and definitely an honor, to be honest, like having an OG and a legend himself here. That also wrote a couple of scripts that we used in the last couple of sessions that we had with Jonathan and Scott, when we were trying to sniff a couple of those serial commands that are going over. And that's also the topic of what we want to talk about today. Like, we want to dive a little bit deeper into the knowledge that you do have, Nebula, and we want to learn a little bit from you, how you did it, how you achieved those kind of achievements that you had done. And I believe it's a perfect start here to have you here.
Perfect. Yeah, absolutely. I watched. Unfortunately, I was not aware about your previous stream until the third one. So I watched the third one live, and then I watched the first and the second one afterward. And so I said, "What did I miss?" I was so angry about myself.
It's we definitely need to gain a bigger audience, but even now we do have plenty of people joining in here. It's lovely to have you guys here and watching us talking and being nerdy as we are. It's lovely.
Yeah, and you guys don't hesitate to comment, ask your questions. You have Scott and Nebula that's going to be definitely able to answer high-level questions. Me and One Clue may be more intermediate. So go ahead. We're streaming live from Twitch, from LinkedIn, from Twitter, from YouTube, from Facebook. So everybody go ahead and give us a thumbs up and comments.
Why don't we do some intros, you guys? Maybe One Clue, you can start off, and then
that's right.
Yeah, I know that everyone is a long-time listener and huge fan.
Yeah, definitely
already know about us in this project, but just in case for the couple of people that might not know.
Definitely, let's do this. So okay, let's start with myself. I'm just a nerd basically. So I stumbled upon the BitX project out of curiosity, to be honest. Like, I'm definitely a nerd, and I studied software development, and I don't know why I do this, but sometimes when I'm bored, I just go over GitHub, and that's literally how I found out about the BitX project. Like, I was going through the most popular projects on GitHub, and out of a curiosity, BitX dropped into my news, or those most viewed projects that I saw for this day. And then I was just looking into it. I was amazed by the first second. I was like, what the heck is going on? I never heard about this. And I never thought about the idea of creating an open source Bitcoin miner. Like, I know that there are a couple of, I know that there are a couple of projects or ASIC manufacturers out there that try to achieve something like this. But for whatever reason, there never has been anything like the BitX project. So that's the reason why I joined in here. And then, everything just kept going. People were joining in, people were interested, intelligent people were joining into this. And I'm just trying to contribute. I'm trying to educate myself, the people. So I do run a YouTube channel, if you're watching this on my channel currently. And what I'm trying to achieve here is to educate everybody of you what's going on. Because I do know some of us nerds know a ton, but sometimes it's just a little bit too difficult to explain. And my goal here is to explain it as simple as possible to all of you who are listening and watching this.
Yeah, so I guess I'll follow. Johnson from Decentral. I'm the founder of Decentral. We started 6th of October 2016. We started, as humble plebs with just one miner, and made our way from there, self-funded. We've grown a lot by our own means. So we're still a relatively small company when you compare us to the other, mining giants. But I think we do have a more and more reach through the plebs, and we're so essentially building and understanding the issues that plebs are having and coming up with solutions for that. And so when we did ASIC repairs, so we started ASIC repairs in 2020, and that's essentially the thing that led us eventually to BitAx, because we were obviously digging to, always digging to get more knowledge and understanding of the hardware we're working with, and stumbling upon the BitAx, just and I was seeing some of Scott's and some of Nebula's miner work, especially with the registers and stuff like that. So this was really mind-blowing for me and eye-opening. It's a whole universe I didn't get exposure to. I'm not from an electronics background, so it's stuff I'm learning a bit by going through. So yeah, that's essentially it. That's what brought me to BitAx, and eventually it turned to understanding that it would, like, to me, BitAx became something that is going to bring back the true nature of Bitcoin and Bitcoin mining. So having each blade being able to be not only a Bitcoin node, but also a Bitcoin full mining node. And I'm thinking of, already some different branches we're seeing, like the Pi hacks. And I do know that this plug is supposed to go back there. We have a fix for that. So yeah, projects like this is just absolutely mind-blowing and super, super important. I used to say that this is more important to me than the S21 and all those new generations coming out. So yeah, that's it.
That's so cool. You guys, both Jonathan and Wanclu, they just like hop into these projects. Like Jonathan, I think I saw that you were getting involved, and the next thing I know, you're like putting together a workshop to build BitAxis, which was just like mind blowing. So yeah, both you guys, super amazing, just jumping in and doing like super cool stuff. So yeah, super appreciative for you guys.
By the way, while you're talking about this, for all the people that are not knowing, you talked like in one sentence about it, the workshops. That's also something that's going to happen. Like this year, I'm traveling around Germany because I'm based in Germany, and I'm doing workshops all over this country. I'm traveling to the south, to the north, to the middle, to the east, wherever I want to go. And basically, yeah, I'm just trying to go around and educate people how to actually solder a BitX yourself, or other projects as well. And Jonathan just happened to display the PyX. That's a project from one of our lovely community members in the OSMU Discord that also happened to created the QX. And if you don't know what this is, it's basically a PCB with 4 ASICs on it, running at like roughly 2 terahash at 50 watts. So it's definitely something cool. He's currently showing like the PyX in the camera. And
yeah, the 204 actually. So this is the one you'll have for your workshop. This is the one that's coming to the workshop.
That's amazing. It's literally amazing. I do love to see this, and I really appreciate it, because to all the people that might not know this, in my workshops, I will have like pre-assembled BitX boards, and then I just educated people about how to actually get started with soldering. So this is friendly from an entry perspective. And in the future, I will add in other boards as like this. Oh, let's see. Oh, seems like the camera does not like it. That's the QX board. And yeah, I will also try to get the people into this as well, because it's definitely something that's lovely to see, lovely to have. Currently, there are just 2 existing QXs on this planet, but I do know that a couple of people are trying to build their own ones. So that's lovely to see. And everybody who can contribute to this overall community, to this movement, to everything that we do is highly appreciated here. So I'd say, Nebula, would you like to start your stream? Because I do know that we want to start with a couple of things and tricks that you wanted to actually tell us about the software and the scripts that you wrote.
Yeah. We can deep dive into the technical if you want. So first of all, keep in mind that all I will present today are not 100% understood stuff. So sometimes I don't have the answer and we have to figure it out all together. I know a lot of knowledge about this chip, but not all of them. I'm not a Bitmain employee. I was not on one of the team of the designer, never. Also, if because of my French stupid accent, you are not able to understand me, don't hesitate to interrupt me. But question, if I go too fast, if I didn't explain something which is evident for me, but maybe not for everybody, don't hesitate to ask me question during the presentation. So I believe that last time you already presented the logic analyzer software from Saleae, which is Logic 2. So we'll not go into detail. I just want to show you that here on the right side panel, you got this extension manager, which is the official Saleae, so the supplier for the software marketplace. And if you want to deep dive into this kind of debug for the Bitmain chip, I would recommend you to install a couple of interesting extension. So the first one is this one, the BM13XX protocol decoder by GP Techino. So GP Techino was my former company when I was in Hong Kong. So you can click on install just like that. Then you can do the Bitmain I2C protocol decoder if you want to sniff at I2C communication from the control board to the APW, so the power supply, or maybe the control board to the hashboard. There is some I2C also in the connector, so you can install that. What is interesting is the baud rate estimate. So this one is another tool, very fancy to estimate the baud rate of a non-known baud rate UART communication. So I will show you how to use it later. Then I did a couple of other, which is interesting. If you look at the FE, where is that? I2C. Hey, you can find it. Maybe I did already install it yet. No. Okay, LM75A. So this one also is one from my coding. This is the driver to understand the thermal sensor into the hashboard. So most of the Bitmain hashboard has a thermal sensor, which are the reference LM35A. So it's on I2C bus, and using that, we will be able, if you click on it, you can have a snapshot of the decoder. So basically, if you put it if you put the high-level analyzer on the I2C bus, you can see that according to the I2C address, which is 48, it understands by itself that it is a LM75A temperature sensor probe, and then it can decode the frame, and instead of having the raw data, 22 there, you have the actual temperature in degrees Celsius. So here is very fancy because you can understand more the temperature inside the board.
And I want to say one thing real quick. These extensions here, and correct me if I'm wrong, but these extensions are high-level analyzers. So like in the case of this LM75A protocol decoder, you still need to have the low-level analyzer running,
Exactly.
which would be I2C. So that decodes the sort of the waveform into I2C bytes, and then the high-level analyzer takes those bytes and actually decodes the protocol.
Exactly. So I will show later how to make the difference between the low-level analyzer LLA and the high-level analyzer HLA. And the last one I want to show to present to the stream is this EEPROM I2C to IX converter. Basically, it takes it construct an IX file, which is a ASCII representation of an EEPROM, basically. So we have some, okay, so it's a standard, sorry. It's a standard representation, which is very handy to extract the data from the trace of the Saleae. So if we, basically on the hashboard from Bitmain, there is an EEPROM. There is also an EEPROM on the APW, and the control board is reading the value from the EEPROM at the start to know what are the specific configuration value for this specific hashboard or this specific APW. So this one will become handy maybe later, maybe not on this stream, maybe on the next one, we'll see. But you can install it for now, and then you are set. So once you do that, let me delete everything I have. I want to start at using the trace that Decentral made on last stream. to show you how we can interpret. So last one was this one, sniffing technique live capture. So if you go to our Discord community, you will see that it's available there. And Jonathan also put it on GitHub. Maybe we'll show later where it is. So if I take the file and just open it, just like that, what I get is roughly the same value and the same timing and the same interpretation that Jonathan was doing that on last stream. So first of all, I'd like to show a couple of quick housekeeping to make it easier to understand later. So we have two traces, two signals, okay? One is the UART communication from the control board to the hashboard, and the other one is from the hashboard to the control board. So the control board, the main purpose of the control board is to control the hashboard. So we can interpret one way of the signal to be the command. The control board is commanding the hashboard, and the other way is the hashboard responding to the control board. So if we are not sure which one is which, we thought about understanding which one is which. I can just look at the waveform, and by scrolling my mouse, I can zoom in, and I can zoom in and zoom in and zoom in, and here I can get some interesting data. If I zoom out and zoom out, here is also another interesting data. So by experience, I can tell that the command from the control board, and they are all the job be sent to the control board to be hashed. So the job data. Why I know that is because the job data is very long stream of data. As you can see, there is each packet of 8 bits. It's a byte. It's encapsulated with a start bit and a stop bit. So it's 8 bits on the line to make 1 byte of data. And this kind of label is the low-level analyzer that Scott presented earlier, because Scott already put an analyzer which is the async serial, just to interpret the raw data, the binary or the hexadecimal representation of the data. So because I know that this long string of data is basically the job data sent by the control board to the hashboard to be hashed by the control board, I know that this channel, if I click on channel 2 here, I can just command rename it in command. And of course, the other way around, the small instruction sent back from the ASICs to the control board is the respond. So you can response. You can call it whatever you like, maybe a reply, maybe command or control, whatever you want. But I would suggest to not use TX and RX, because TX and RX is the way to name from the point of view of one end of the signal. Basically, the signal, if I just consider the red one, it's the same electrical signal from the control board to the hashboard, but it's the control board is outputting the signal, so it's a TX from the output from the control board, and it's a RX received from the hashboard. So if I put a name on the line, and I don't want to take a point of view of either hand of the line, so I want to take a meaningful name which is the same for either hand. So I don't want to use RX and TX, because doing that you will have trouble later to understand which is which. So if we just keep this name of command and response, is much easier for the later analysis. Then I can do the same also for the. So if I just remove what Jonathan did last time, just to make it new, if you go to the first tab, which is the analyzer tab, you can make an async serial I2C or SPI bus, and there is many more by default on this kind of tool. But the three main one are this one, async serial for UART, I2C for the synchronous bus with 1 clock and 1 bidirectional data. And the SPI bus is a synchronous bus also, 1 clock, but full duplex, meaning that both sides of the link can talk at the same time, because each one has a separate line. So it's a more advanced and more another bus. So we just focus on the async serial for tonight.
Can I
Async
just
serial,
give a
yeah.
quick bit of context here about where this async serial data came from?
Yeah, sure.
So this, this came from our stream last time, but essentially what you're looking at here is a logic analyzer capture of the data going back and forth between the control board on a miner and the hashboard on a miner. And so this is the async serial data, which is specifically talking to the chips on the hashboard. So there's a big chain of like 100+ chips, and you're looking at the commands from the firmware running on the control board to the chain of chips on the hashboard, and then the responses back from those chips. And so this is the mining. This is mining. The jobs that Nebula mentioned, that is work going from the control board to the chips saying, here's the block header we want you to hash and look for a nonce that meets the difficulty. And then the responses are if the chips, the mining ASICs, find any nonces that meet the difficulty. So that's when it responds.
Yeah. So basically, while Scott was talking, I got a crash of the software because this trace is so long. Look, there is tens of seconds of data. So at the normal human scale, tens of seconds is nothing. But if you look at data which is on the megahertz, meaning you can move 1 million times per second, then we get a lot of different value. And this is memory, a high usage of the memory. And sometimes the software is crashing or your computer is not handling properly. So what I did is I did have a crash, so I did have to launch again the software and to open again the file, but I did not save it. So I would recommend to save it as often as you can, like that, or maybe Control S, which is the same as saving, to save the progress we did. Okay. So now I want to use an async serial because I know this, as Scott mentioned, this signal as asynchronous serial communication from the control board to the hashboard and from the hashboard to the control board. And if I put to add a new analyzer, the software is asking me on which input channel should I put my asynchronous serial analyzer. So let's do the command first, or maybe the response because there is less. And then he wants me to input the bit rate. So the specificity of the asynchronous serial is to be asynchronous. It means there is no common clock between both ends of the communication. And so to understand each other, both ends should have the same baud rate by configuration. So it's a fixed configuration to put the baud rate. If you don't know the baud rate, like last time, you have to figure out the baud rate. So let's say I do a cancel there. I want to show you how can you estimate the baud rate with the extension I just installed a few minutes earlier. So if you go there, I zoom on the oscillating value, and I can do a measurement. Okay, I do a measurement. I click a plus, or I can do that here, measurement, and I swipe over the interesting data. Here I got some interesting data, the delta t, which is the period of time where I am looking at, so the highlight period. But if I look here, I got the F baud, which gives me the baud rate, estimated baud rate of the data. So here, 13 megahertz is way too high. So I guess I did it wrong. I should have this kind of value, 13 again. No way it's 13. Okay, so this is the demo effect is not working because it shouldn't be 13.4 megahertz. We don't have any.
What's the sort of bit time, like single
Yeah,
cycle bit time?
18 nanoseconds.
Okay, so that's right.
Yeah, that's right. That's 12.5 megahertz, which is 6.5. Yeah. So one way I was doing is like that. but it's very approximative, and maybe sometimes it's failing. So I don't know if I can recommend that, but it was useful for me in the past. Maybe look, here I have 12.5, yeah, 12.5 megahertz from the command, and so we can estimate the 12.5 megabyte per second. So now we can do the async serial on the response and put the 12.5, which is a good value. So 12,500,000 bits per second. You don't have to change anything. And what I would recommend also is to untick this to one, because I will show you what is the protocol result table and what is the terminal. And for this kind of low-level analyzer, we don't want to be flooded by data. If I tick on that, I got here. So basically, this is the table where I get for each byte of data. Let me zoom on one frame. Okay, each byte of data, I have the type, the start frame, so the timestamp, the duration in nanosecond, and the data itself. But these are the raw data. So raw data, if you want to be hardcore, you can try to understand binary, but that's not the purpose of this today's stream. We want to go high level. So the best way is to just on the low level analyzer to untick the show in data table. And the same for the terminal. Terminal is there. We got a lot of raw data in the terminal. It's not very useful. So we can just untick so okay, now I have to clean the terminal. Okay. And then if I want to make a high level analyzer on top of the low level one, I can add another analyzer. So basically we are talking about UART communication. So we'll add my BM13XX protocol decoder. You want to know on which input analyzer it will be applied. So it will be on the, okay, so async serial. Here the naming is not very good. So why not, by the way, renaming the async serial one, because when we'll have two of them, then we don't know which one is which, once again. And then I can do here, and I took the async serial response. So here, my configuration tool is asking, can you, by default, give to the tool which flavor of the BM chip it is. So I just have the old one, the BM1385, for which the datasheet is online. So Bitmain released the datasheet many years ago. So it was the first protocol where the datasheet was public. So I did develop the first version of this one, but now it's pretty outdated. Maybe it was the S7 generation of miner. So it's pretty outdated. The BM1397, which is the S17 generation, so the one used by the BTAX Max. And now we made an effort on the BM1366 for the BTAX Ultra. In between the 97 and 66, there is a lot of different flavor. There is 98 for the first generation of S19, and then the 60, and then the 62, and then the 66. All these are from the S19 generation. The 19 J Pro, the 19 XP for the 66. The 60 was for the 19 J, not J Pro. So anyway, there is a huge mix of BM variant into the S19 generation of miner. So if you don't know, you can just pick one and you can try it and you can change it later. And if maybe it's not a good one, for this one, I'm sure that is not a good one, because the S19 J Pro, on which Jonathan did the capture of this trace, is using the BM1362.
Yes.
So I don't have any 62 on my protocol. So we can expect some bad analysis because the software is not basically done for this one. I didn't do that because I did focus on the one that BTEX was focused on. But maybe we can, with joint effort with other people on the community, we can develop other analyzer for the in-between version. So if I take the 66, which is the closest to the 62, here you want to know the mean state count. So the mean state count, maybe this naming is misleading. So maybe I could change the value. because the millistate count is basically when the hashboard, the control board is sending a job to the hashboard. As I showed you, the hashboard, the job sequence is a lot of data, and inside they can have multiple millistate. This is the technique it was called ASIC boost previously in mining industry, so that the chip inside has many core. Okay, it can do many computation at the same time, just like multiprocessor in a normal CPU. But each of these core has also small core, and the small core is called ASIC boost. So basically, you send different millistate to the chip, and the chips spread the different millistate to the small core inside each one of the core of the chip. So there is a lot of hierarchy there and a lot of abstraction that you need to be understood. Maybe at some point some documentation should be written for that. But if you don't know, you just let by default one, and I will show you later how it is important to change it, but it's not very important. And then you have CLKI, the clock input frequency, which is the value in megahertz of the oscillator, which is provided to the first ASIC on the chain, on the hashboard, and it's propagated to all ASIC on the board. So this clock input is very important because it's the source of the internal PLL. So the PLL is the phase lock loop. It's a kind of circuitry inside the chip to elevate the frequency from a fixed frequency of 25 megahertz or any one to a higher frequency. So basically the ASIC is using 4 PLL inside, the PLL 0 to PLL 3. So it's not using 4 PLL. It has 4 PLL inside, but only using 2 of them. One to elevate the 25 megahertz to the baud rate you want to communicate for the UART protocol, and one for the SHA engine, also for the hashing engine, to hash at a higher frequency. So basically, when we said we put the miner at 400 megahertz or 600 megahertz or 550, this frequency is derived from the clock input. So on all Bitmain chip, on all Bitmain hashboard, there is a 25 megahertz oscillator, which is the source of the clock for all the chip. On the BitX also, we put the same 25 megahertz value. But if you want to experiment with another clock, another oscillator, you can put 20, you can put 30, 40, whatever you want. Then you have to adapt everything in consequence. So the high-level analyzer is based on that value. And by default, you should stay at 25, but you can experiment with different value. Here again, I don't have any need for the terminal because I will put all my data into the protocol result table. So I just keep the protocol result table ticked.
Hey, Nebula, why does the ASIC clock-in frequency matter for the high-level analyzer?
It's not useful for the high-level analyzer, except for the fact that it will. Okay, when the command is sent by the control board to the hashboard to change the baud rate of the UART, or when the command is sent to change the internal frequency for the hashing, then the high-level analyzer is using this raw data, and you need the clock input to scale it to the actual value. So the main purpose of the high-level analyzer is to display a meaningful value for the hacker to understand what is going on, to not deal with the raw data. And the raw data is just containing the multiplier. So we don't have the base frequency. So that's why the high-level analyzer need the base value, and it's almost every time 25 megahertz, but I needed a parameter so we can experiment with different value.
Oh, that's so cool. That's so cool. So if I understand that right, it's so the high-level analyzer can decode those registers for the baud rate. And in order to decode it, it needs to know the clock frequency.
Exact.
Ah, that's amazing. You're a genius.
Exact.
It's like a baseline, right?
It's a base frequency. So hardware is using a base clock, and it scale up this base clock with the PLL, and the scaling factor, the ratio, come from the control board from the protocol. So on this line, we just have this scaling factor. We don't just have the ratio. So if we want to display the actual megahertz of the core or the actual baud rate of the data, the new baud rate. I need the base clock. I need the base frequency to make the calculation, just like the chip is doing. That's why I make the value.
When we're speaking about this base clock that's used on those bitmain chips, I was also wondering about this. Like a couple of people asked me when I was talking with them about the bitmain chips, that you cannot just snip and ramp them up to like 550 megahertz or whatever you want to use on them on a megahertz wise. But why actually is this? Why can't you just use an ASIC chip and use it on a specific clock rate from the beginning? Why you need to ramp up those chips? That's something that I don't really understand, to be honest.
Okay, so any chip, so the Bitmain ASIC or maybe your CPU or any chip you can find on the internet on the market, it's a piece of silicon and there is some small security inside. And when you make current going through the silicon, it produces some heat. So everyone there know the Ohm law, and the power dissipation from the chip is very important, especially for the ASICs. So if you, just like a CPU, if you want to overclock your CPU, you can overclock it as soon as you can extract the heat efficiently. So that's why the hardcore overclocker are putting some liquid cooling to be very much very effective on the heat dissipation, so they can raise the frequency and so the temperature of the chip. That's exactly the same for the ASICs. If you want to hash quicker, you have to elevate the frequency, but at high frequency you will have high number of change state internally, so high number of heat dissipation. And if you are not able to dissipate the heat efficiently, then you will go into thermal breakdown and you may damage the chip. First, it will stop working well, so it will hash garbage data and display and give bad nonce. But after that, if you go further, you can totally destroy the chip.
Or so it's basically just like some sort of a control mechanism or a safety mechanism for the chip to not actually kill himself instantly. Just like, okay, we try to over time go to specific frequency, and then we see if you run unstable or so.
There is not such a protection inside the chip. The chip is dead stupid, and if you ask him to kill itself, he will do it happily.
Yeah, obviously, but it's the reason how you program it, like to actually ramp up slowly instead of going full on a specific frequency instantly.
The ramp up slowly stuff is because the phase lock loop, which is the multiplier of the frequency inside, need to stabilize itself, and basically the firmware of the miner, the original miner or maybe the Brain OS or the Luxor miner, are doing the ramp up slowly just to test the actual hardware, because the software is not aware about which chip. There is hundreds of chips inside the hashboard, and which one of these chips are very performing good and this one are not performing good. So you want to do a fine tuning to find the sweet spot for the actual hashboard inside the control, under the control. So it's a kind of very interesting, very high technical way of fine tuning, because if you just put a lot of megahertz and a lot of V-core voltage, then you will produce a lot of heat, and a lot of hash, but the efficiency, the overall efficiency will not be very good. So you will not obtain the 20 joule per terahash target, or maybe less, that the chip is able to do. To have the best efficiency, you have to find the sweet spot, which is not the highest frequency. It can be the lowest frequency or maybe the lowest voltage, at which the chip is still working, functionally hashing. But so basically the software is ramping up the frequency to find that sweet spot for the actual hardware is controlling.
If the viewers want to dig a bit more, I guess on that topic, they can go, and it's more general, but you can have a look at the Silicon Lottery concept, where I guess this is what we're referring to here, where the firmwares, they do have to go through a tuning process to figure out a bit which chips are weaker and stronger, and that's just something. Even new chips, they come with that concept of silicon lottery. Even your GPUs and CPUs, they have that concept where there's imperfections in the quality of inscribing, you know, those all those little circuitry inside your chips. So I can't recall the exact name right now, but that being said, there's that concept where there's a varying by small degrees, but in ASIC, since you're pushing the machine always at 100%, those little imperfections, they might be a little bit more perceptible, right?
Mm-hmm. So going back to the protocol analyzer, what I did was adding the high-level analyzer on top of the low-level analyzer. So once again, I used to name it with the resp suffix, so we know we are talking about the response line. And what I can see that here I got the value in the data table, which is interesting. Some value are not very interesting, so I can just hide the column by right-clicking on there and removing the start. I don't have the need for the start, which is the absolute value of the trace. There is no meaningful value there. The duration also is not useful. The frame tip. So if you want to dig deep into the protocol, there is two types of frame, the fixed input length and the variable input length. So if you want to learn that, you can just look at the documentation I wrote on Scott GitHub repository BM 1397. But I don't need it for today. The command also, there is some command which is broadcast to all the chip on the chain. So we have all, and some of the command are sent to a specific chip on the chain. So all on one, so you can understand if you want. I don't need it. The command also, so it's the raw value of the command, but it's much more interesting to use the type. The type is the understandable value of the command, so I don't need it. And I will keep the chip, the register, the value, and the last one. Okay. Here I can see I have strength data. So as you see, after adding the high-level analyzer, I get this H1 analyzer there. I can move it just above the data line, which is related. So it's very easy to understand. As I can see that now the value is going over the frame. So I have an error there. It's because the trace was started in between of a communication. So we have an asynchronous asynchronity. So what I used to do, as I told you earlier, this trace is from the hashing period of the miner. So the control board is continuously sending some job, and the hashboard is responding some nonce. So we don't have the need for this 100 of second. We can just select a handful value. Okay, if I do click, right click, and delete data before this point. So I'm not clicking in between the frame. I don't want to cut a frame in between. Okay, and then I will do, maybe I will keep 2 or 3 hash. Okay, I can cut, delete data after this point. So once I do that, I can see, oh, sorry, that's not what I want to do. I can save again the capture, but I don't want to erase the old capture, which is the big one. So I can add a small section.
So Nebula, I'm right that the saves you're making right now, the naming you gave to those signals and those changes when you remove parts of data, they're going to be part of that new SAL file that you've just made, right?
Exactly. No, I did remove the data from the left and from the right. I just select a meaningful. I can do that also with the time marker if you want to add a marker pair. If you want to focus on this data, so look, I will do from here to here, and then I can click on right and delete data outside of the pair. You can do that if you want.
Got it.
Okay, so it's very easy to
narrow
down, yeah, and then you save as under the new name. What you can do also is open the new name, the small section I just created, which is only 137 kilo instead of 40 megabytes.
Yeah.
And then you can close the old one and we can just work on the smallest one.
Nice.
So here, what's wrong? I have synchronicity, means the high-level analyzer is start at the same time as the low-level analyzer, but you want more byte, basically. Why does it want more byte? It's because I was selecting. It was because I was selecting the 1966. Okay, edit 1966 instead of the 1962. And the technicity of the difference between both is that the 1966 is using version rolling, and the 1962 is not using version rolling. So because of that, the hash, the response, the nonce response from the hashboard to the control, so the response we're talking about, contain an extra data, which is the version rolled inside the chip. So the hashboard can reconstruct the mid state according to the version rolled inside the chip. So if I want to understand properly this answer, I should select the 1397, which is not using the version rolling stuff. Here, look.
Hold on, this is an interesting thing. So, I mean, we can essentially confirm that it's not doing version rolling because of the high baud rate, right? We had that like,
exact.
Right, then we had like 13 megabaud or something like that. So that's just from experience, that's a sure sign that it's not rolling version. But I thought that the S19J Pro did roll version.
I think he's able to do, but it's up to the firmware to use it or not.
Oh, okay. Interesting.
Yeah, really interesting.
Yeah, I did found into the original S19J Pro firmware by doing reverse engineering. I did found this register A4, which is used for the version rolling. So the code is aware about this register, which is for version rolling, and which is exercised into the XP firmware, but it is not using it. So I think the firmware has the code inside, the chip has the register, but he's not using it for whatever reason. I don't know. Maybe because
so you could argue that maybe they just hold the version rolling back just to release another new miner that's actually just the same but with version rolling.
Yeah, maybe there is some bug in the silicon.
Yeah, or a bug in the silicon. Sure, it could also be that the chips that are specifically used in the S19J Pro are not as performant as in those XP ones.
I wonder what firmware was this? Because I know Jonathan, do you remember? Was this Brains?
Yeah. So normally this one was Bitmain, if I read the description correctly. But we did have a few captures with Brains as well, and I did get the Commander license now from the team at Luxor. So we're going to be able to make the captures for using Luxor as well on all those different models, right? I guess we should, and that's going to be one of my goals. I'll put it in the GitHub that's being shared just a bit before Hashboard captures. We'll just have the whole 19 series run with all available firmware, so we can interpret how they're working. For instance, that feature we've discussed about the real-time frequency adjustment is really interesting. But it's really interesting to see, because I do remember from one of our previous stream, like you, Scott, that from what I remember, we had figured out that the 1362 was using version rolling. So I'm wondering if it was not from our Brains OS capture.
Yeah, it must have been. It must have been from the stock firmware that we did that, because I remember that too. We clearly got a capture from a J Pro, and the baud rate was much more like 1 megabaud, which.
Well, I'm thinking it's from our Brains capture and not from the Bitmain capture.
I think this one must be the Brains one, which is very interesting that they're not rolling version. I mean, also, this is kind of an interesting thing that I've wondered about a lot is, there's the different control boards you can get that have the different sort of processors on it, right? You can get the Xilinx Zinc one, you can get the Amlogic one, you can get the BeagleBone one. I don't think that the Amlogic control board is capable at operating at a high enough baud rate to work on machines that don't roll version. What do you think about that, Nebula? Does that seem right?
So I know for a fact that the 12.5 megabaud per second, which is the highest baud rate I saw between the control board and the hash board. So doing a UART at 12 plus megabit per second is already a high speed baud rate.
That's
We can do 25. It's possible. The next step
Really?
is 25. Yeah. Some CPU can do that. Some STM32 can do that. Some I did the exercise in the past. Some UART at higher frequency, but then because you don't have any synchronous clock on the line, you are very prone to error and to miscommunication.
Yeah, that's what I would think.
Yeah. So putting to the limit at 12 megabaud per second is needed because if you have a very efficient chip, it will roll the non-space, it will hash the non-space very quickly by the number of the internal core and by the number of the frequency you can do. And so you need to feed continuously the job at a very high frequency rate. Basically, this one is feeding, look, I did put a timer marker pair, hard marker pair, at this job command at this one. And it's only 524 microseconds between two jobs. Means the chip, or not the chip, the hash board, the full chain of the hash board, is able to hash the full non-space without version rolling is only half of a millisecond.
That's insanely fast.
That's insanely fast. So that's why if you want to give the same amount of data at this frequency, you cannot have a lower baud rate because if you divide by 2 the baud rate, if you put a 6.7 megabit per second, then your frame will take double time. And double time, you will have you will have this frame. Look, I just have 255 left of unused data, and the frame is also already 268. So you don't have any bandwidth on the 6.6 megahertz to put the same job at the same rate to feed the chip continuously. So you have to higher the baud rate. But when you higher the baud rate, then you hit a wall, which is the baud rate frequency cannot be as high as you want because of the noise and everything on the board. So that's why they implement now the version rolling so that the chip can roll not only the non-space, which is 32-bit, but also some bit inside the 32-bit version, 16, 15 bits, so they can multiply by that much the overall hashed space. So they can. So now we know with Scott we discovered that the 1966 of the S19 XP is sending a job only every 2 seconds. So 2 seconds compared to the half millisecond, it's a huge difference.
Yeah, it's kind of insane to think about, like the fact that the chip can get through the 32-bit nonce space so fast that it'll get through the entire space before the control board can even finish sending out the work.
Mm-hmm.
It's kind of wild, right? And you end up with these really high baud rates that, like you were saying, are just sketchy, right? Because we don't have a synchronous clock to keep everyone in line. They have to, each side of the serial communication has to sort of reconstruct that clock. It's really wild to think about, and we kind of hit a wall, right, with these chips getting faster and faster, and the hash boards getting faster and faster. Is that
exactly?
We just hit a wall with the serial communication, and they had to do something. And version rolling is a good option. You could also do time rolling, things like that. But it's a wild engineering problem. It's cool.
Yeah.
One thing that comes to mind too is that we have JPro. We might be working a bit against us, right? Because we have 8 different hashboard revision for the JPro, and amongst those there is also the no pick revision. So I'm thinking that maybe some different captures based on pick and no pick might also, who knows? Maybe even with the same firmware, you're getting version rolling and not depending on the version of hashboard you're actually running.
I know there was a big difference between the what was it, the the 1362 AK and one of the other ones. It was like the chip itself was physically smaller, less pins. Like it wasn't just a small revision change. It was like a totally different chip, even though they were both
and aluminum boards too. We like those.
That's right. So
that's why if we want to be very precise, when somebody on the community is doing a log, is tracing some data from any one hashboard, we need two inputs with very good accuracy. One is the hashboard revision. So usually it's a BHB and then some number. So we know which revision it is of the hashboard because there is different variant of the same hashboard for the same miner. And then we need the firmware and the version of the firmware. So if it's Bitmain or BrainOS or whatever, then it's useful to know these two values, one for the software, one for the hardware.
And I'm thinking, would it be useful to also gather information such as the control board used, right? Because you have all those different control boards too that might have a different behavior. And then I'm wondering, like, I guess the bin of the chips shouldn't matter because that's just different quality, let's say. But the type of the chips, so let's say S19XP, you have the AL and the AG revision. So is that something that might have some influence that we can perceive from those captures?
Of course, there is some influence, but the firmware from the control board will adapt to that and to send different value to the chip. So it will not exercise at higher frequency or higher voltage, or maybe it will not use at all the version rolling. We will talk about the fact that the 1962 is able to do version rolling, and some firmware are doing that. Maybe they are able to do that only on specific bin of the chip. If you make 1 million chip production, and you got 20% where the version rolling is bugged, then you can just put this one in a bin and make a specific firmware to can detect that and not use the version rolling at all, but you can sell the chip anyway.
Makes sense. Makes a lot of sense. So I guess the best is to gather all the information, right? So we want the BHB hashboard revision number, we want the control board type, we want the firmware that's being used, as well as the chip type that's populating the hashboard.
Exactly.
Do we have any indication that the chip variant is included in the hashboard model number, the BHB number?
Okay. So it's a very technical question, and I have some clue, but not a firm answer to that. And we can discuss that with the fact that when the control board is reading the EEPROM from the hashboard, there is a lot of data inside that. And it's another whole rabbit hole. So
if you look here, this is the label where you'll get the different naming schemes and the bin numbers we're talking about. So let me try to take a pen there. And it's going to be difficult for me to show you on screen, I think, but there you go. So this here, it might be hard to read, but you have the BHB version of the board. So that's the model of the board. In this case, it's a S19K Pro. And this is the label where you'll find the chip information normally. So it's hard to read on the screen, but it's saying it's a bin 4. And the chip type, I've never read actually from those K Pro yet. So I'm not sure exactly which one is what, but normally on that label here is where you'll find the chip type, and so you just need to find exactly like which characters to read. So this specific hashboard I don't know yet, but on the other J Pro, which I don't have in the office right now, you'll see something like a 62AA, 62AC, 62AK, and those are the 1362 variants we were talking about.
And by the way, BHB, I assume that it stands for Bitmain hashboard. And if you look at the Hydro miner, they got a HHB, which is Hydro hashboard.
So what would be NGS for? Because they do Bitmain, they also have those NGS specification, but I think it's for like L7 and stuff like that.
I don't know which is. No, there is some Bitcoin related NGS also.
NGS2, huh? Yeah.
I don't know exactly what they are for. So going back to the analyze, if you agree.
Sure.
So just by changing the fact that it's not using version rolling, now I have the protocol analyzer is aware about the actual frame, and it can show you these specific nodes. So we got 3 nodes on the narrow down 1, 2, 3, only 3 nodes. What I can do is double click on this arrow and go zoom into it. Very easy. I can go to the next one if I want, or I can use this small to find the next. So we are very handy shortcut. And here in the table, we have some interesting data. So it's a tip nonce, okay? The value is there, so that's the nonce value. But I got also the job ID, the mid state ID, because basically, when we see the job command above, each job has a job ID, and if the control board wants to know to which job this nonce is related, you need to have the nonce value, which is 32 bits, but also the job ID and the mid state ID. So we can reconstruct the correct or the header candidate to be sent to the pool or to the full node.
So that job ID might relate a little bit to Crypto Ice's question, which is, are we sure they don't have any memory buffer on the hashboard? Will the chain contain multiple job IDs at any given time?
No. Each of the job here has a different ID. So it's incremental from 1 to 4 billion, so 32 bits, and then it rolls again. And no, maybe not so much, but we'll discover that together. Look, I will make a new analyzer, async serial. On the command side now, I don't want to be flooded by data. So this one is the command cmd. I'll put another high-level analyzer on the command side, so I know it's that. And okay, I let the mistake count at 1, and we will discover it's not a good value, because I know for a fact that this chip is using a high number of mistakes. So here we got some nonce. Let's look at the first one, maybe this one. No, the first one. And oh, my analyzer, my high-level analyzer, is not perfectly in sync with the frame. This is because I put only one mid state, and the job contains at least 4 mid state for this one. So you can poke around, you can try to different value, but if you discover that you have a misalignment, it's because some of the what I did. I have a bug when I stream my edit. If I put 4 there, no, it's not 4. Maybe it's 8.
So is that a trial and error process? Is there any way around trial and error to figure out the number of mid states, or how did you figure it out?
Yes, there is a lot of way to do. If you reverse engineer the firmware, then you can find some topologic file into the firmware starting at the S19 generation. And on this topol.json file, you have the number of small core. And the number of small core is the number of ASIC boost. So it's the number of mid states they've sent in parallel.
It's pretty cool. If you SSH into your miner with the username miner and the password miner, you can get into the file system of the control board. And I think it's in /etc. But if you look in there, there's a file called topol.conf, topol, which I assume is short for topology. It's a configuration file for the particular hashboards that the miner has. And in there, so this is what Nebula was alluding to, in there you will see the number of big cores and small cores. And small cores corresponds to the number of mid states that the chip supports.
Yeah, the number of ASIC boost. So I did try different value, but I didn't get a good alignment. It's because the analyzer is not aware about the 1962 just aware about the 1997 and the 1397 and the 66. So we have some more effort to do on that one. So the job format is not one of the two non-job format. So we have to understand a little bit. So, but some of the format are the same. So we can see that there is some job ID 6072. The next job ID will be, okay, so we don't have an alignment, so we cannot rely on the value. But we have some mistake count, 8. Okay, we have 8 mistake count, so just put an 8 here. Eight mistake, the n bits, which is the network difficulty, the n time, which is the network time for the block candidate, and then some CRC. And I didn't display all the mistake because there's a lot of binary data, which is not very useful.
And what do you know? That was the date of our last stream, right?
Exactly. So if you just keep the raw data, you have the 32-bit value of the epoch time on the end time, but the high-level analyzer did calculate, display the date at a human understandable format, which is 16 January 24, which is the last stream at UTC 8 p.m. Exactly. Because we are doing some real hashing. Jonathan, you are not a faker.
vperm2f has a pretty good point. That the ASICs that get mid states don't do version rolling. That's correct. So if you have a chip like this one we're looking at here that is not doing version rolling, then you actually have to send the mid states, the pre-calculated mid states, in the job. If you have a chip that is doing version rolling, you actually don't have to send that. It makes the job a lot shorter because the mid states are generated on the chip. And this is what vperm is also saying, which is correct, is that if you're rolling version, that actually affects the mid state. So the mid state is just the first part of the hashing function, which is double SHA-256. So the first half contains the version, and I believe it contains like 4 bytes of the Merkle root. It's kind of a weird way they split it up, but that's a long way of saying that yeah, the
block header, the beacon block header, which is part of the main consensus since the beginning of Bitcoin, is composed by the 4-byte version. Then there is a 32-byte Merkle root. No, the previous block hash.
Right. Yeah.
Then there is 32 bytes of Merkle root. So the Merkle root is the root of the Merkle tree of all the transactions inside the block. Then there is a 4-byte n byte, which is the network difficulty. Then the 4-byte n time. Then the 4-byte nonce. And so if you do SHA-256 on that, SHA-256 should be done on 256 block at a time. So you have to take the first 256 value, and because of the first value, which is 4-byte version, the 32 bytes of what is it yet? Of the previous block hash.
No, it gets the whole previous block hash. It's 4 bytes of the Merkle root.
Yeah, and then you take the first 28 bytes of the Merkle root into the first segment of 256 bits. Yeah, so there is a misalignment there. That's why the CPU or the pool is pre-computing the first round of the SHA-256 for the hashing, and it gives just a mid state. Mid state is the intermediary state of the first block, which is already hashed. But because of the version rolling in the chip can be done now, we cannot provide the mid state because the chip should be able to change the version, and the version is the very first field in the header. So you need to provide that in the job data. not the mid state, but the full header value. So the chip can compute his own mid state by itself, according to the version rolling he's doing internally. So that's why
essentially the before version rolling on the chip, the way you would generate new work for the chip is you would roll version like in your firmware, and then you would pre-compute the mid states, whether it's 4 or 8 or whatever, and send those out on the chain. So it's just kind of move that that task from the firmware on the control board to actually on the chip, which is pretty cool.
Exactly.
I mean, it actually makes sense. Like, you don't want to, in the end, have like a big ASIC chain on your board, and then you need, I don't know, like a supercomputer to control all of them because the baud rate is insanely high. It's just a brilliant idea to do it like this.
Yeah. So going back to the analysis of the data, on this trace, I don't see any more interesting way of using the tool to show you. We can deep dive into the job format. So the job format is not one of the one which is fully understood by the high-level analyzer. And the high-level analyzer is the same comprehension of my reverse engineering of the official Bitmain firmware, which is also fully documented into the Scott repository. So because of that, we don't have a full comprehension of this BM62 chip. But what I would like to show you is take the capture from the stream, which was on December last year, also from Jonathan capturing on this S19J Pro also with some auto tune. Let's open that. This one is much more interesting to me. Why? Because this one is starting from the start. So I can see there a lot of hashing. Okay, so these are the job. The job are very small and are spaced by almost one second, 700 milliseconds. And we got a lot of hash because now we know that there is some version rolling inside. But the very interesting part is the beginning of the setup, when the control board is setting the full hashboard and putting all the ASICs configuration into the hardware. So this is very instructive for us to understand the protocol because we need to understand that very precisely to be able to make a firmware for the BTAX, to make some fancy frequency scaling or auto tune, or maybe lower the consumption so we can adapt to the solar production. This kind of doing is only because we fully understand the setup phase, not the hashing phase. The hashing phase is only 20% of the job. 80% of the protocol is on the setup phase. So once again, I don't want to have the full setup. So I will delete data before this point. And I will keep only there, the few first after this point. Okay. So now I can save, capture, and call it step 1. We'll subdivide later. Call it step 1 first. So once again, CMD, some housekeeping, RESP. On the logic analyzer, I don't know which one is which one. So edit, this one is CMD. CMD. RESP, perfect. I don't want to have noise from the low level analyzer. So I can untick this to 1. And I can start adding my BM protocol. So first the command, always the most interesting. I have a choice. Let's try 66. I know it's not good, but we'll try that. We keep the mid state. So mid state is not very useful. It's just for the hashing stuff. Here, what I get is first, if I look at the very first frame instruction sent by the control board, I have again a misalignment. So let's try our 115 kilobit per second. So these are this is the standard baud rate. So let's try that. Let's change it. And now I get the data. You see? I can remove. I can delete. I don't know how to do. Let's do that like that. Delete the measurement. I don't need it anymore. And I do the same for the response side. Response. Put my H1 over there. Resp. Command. And I should have, yeah, the response also. I should change the baud rate. Here it is. Now we have, look, each command on the initialization phase has a specific length and the response also. And by looking at the data, it looks pretty sharp. We will discuss the protocol later. But yeah, oh look, now it's okay. I still have some frame. At some point, yeah, over there, when there is a big gap, usually, is to let the protocol change the baud rate. Oh, here my command, my byte is not the same as the. So the software, the control board did ask to the hashboard to higher the baud rate to an unknown value. We'll discover that later. So we have a different baud rate. In that case, the logic analyzer protocol, the tool, is not able to do dynamic baud rate change. So what we have to do is to put a marker between the change of the baud rate. Let's put it right in the middle. I can save my capture into step 1. Okay. I remove delete data after the marker. No, what I do? I delete before the marker. Okay. Now I can save the changing to step 2. I can open my capture step 1 and step 2. Step 1 first. Step 2. I can close my previous big one. I just have the step 1 and the step 2. Step 1. Yeah, basically I just want to split the SAL file, the SAL file, according to the baud rate. So what did I do? Oh, it was not saved. I don't have any. Oh shit! Sorry. Okay, I did. I changed the name. Delete data after. And this one should be saved into step 1. Step the true one. Yeah, I messed up with the name. Anyway.
Housekeeping, yeah.
Housekeeping. So this step 1 is the baud rate is 115,200, and I get all the data there. And the step 2, the baud rate was increased. We don't know yet about the new baud rate. So we can discover the baud rate by looking at the bit timing also. But I want to show you another example of the high-level analyzer usefulness. Is that if we look at the frame, so once again, I don't need that. I just need this one. chip also, I don't. Okay. So the register. So during the oscillation, the initialization phase, the control board is setting up a bunch of register. Okay. So the first one is write the register A8. So let's look at that. And A8 is the, I don't have a name for this one, so I put A8, which is the register address. If we make progress on this register, maybe we will learn more and we can put it a new name. The version rolling there is the A4. So we get A4 value, which is the address of the register. Miscontrol. So this value will come from the reverse engineering of the bitmain chip. We got some baud rate there, calculation, 1.62. So he proposed you a new baud rate, but it's not true. So the baud rate on this chip is not the same as the 1397. The interesting part is when when here the read register chip address. This command is sent to all chip at all, means it's a broadcast command, and the control board is asking to the full hashboard, who are you? And then it's only one command sent to the full hashboard chain, and all the chip are responding one by one. Look, who am I? I am 1362. So you give back the value of the chip. And you get 1, 2, 3. You can try to count them. You get one response for each chip on the chain. So the control board is able to count the chip, and then you will be able to divide the node space according to the chip count on the chain. So this is interesting info.
The Nebula, that part here, is that the part where when you're looking at the mining log, from your machine launching, it's actually doing that chip count. So is that what we're seeing here, but on the signal side?
Exactly.
Got it.
Exactly. Your firmware is doing the basic test on each of the 2 or 3 hashboard of the miner, and then it wants all the chip on the hashboard to be enumerated. So it just send a broadcast chip address request, and all the chip are saying, "Hey, I'm here. Hey, I'm here," and they're all the same value, of course.
And as a follow-up question, like the chip address is something that I've always been wondering about. Is that something that's hard-coded, or is that like a bit like an IP address where it's self-attributes, or there's like how does the chip addressing works?
Okay, so a chip address, it's a logical value. It's configurable by software. So by default, all the chip on the chain has the chip address 0. And when they reply to the chip address respond, they all give 1362, which is the identification of the chip, okay, the version of the chip. 03, which is the, okay, so this value is still subject to discussion. I don't know exactly what it is. Maybe it's not used, maybe it was used in the past and not now. And the 00, the 2 last one, the last byte, is the chip address. The chip address on the bitmain chain is only 1 byte. So there is only 256 value from 0 to 255. And by default, all the chip have the chip address 0. So that's the responsibility of the chain, the hashboard, to assign new chip address to all the chip in the board. It's just there. Just look at this one. They do a chain inactive command, so they don't want the chip to propagate the value to the next chip because they're all in the chain. So they send the command 3 times to be sure that the chain inactive is propagated to all the chip in the chain, and then it starts to give chip address. So you have a chip address 0 first, chip address 0, which is only listened by the first one on the chain because the chain is inactive. Okay, and as soon as the chip received his own chip address, so it's just like an IP address, it's the logical value, software value that can be assigned by any value to any chip. But when the chip received his chip address value, then he starts propagating the next command to the next chip on the chain. And the next chip address is 2. And then we get 4. And then we get 6. So there is an increment of 2 for each address, chip address on the chain. It's not hard coded. It's not pull up and pull down on hardware is given by the software. And we are
So it must, once it gets an address from the set chip add command, it must activate, right? Because it's going to need to start passing data to the next one.
Exact. It activates itself and it starts communicating the value to the next one.
It's amazing how like integrated these chips are. Like they are absolutely designed to be connected in these long chains. It's pretty neat.
Oh yeah, well designed for that. And by the way, why do we have an increment of 2? Maybe they should have put the chip address 0, 1, 2, 3, 4 by increment of 1, or maybe by increment of 4 or 8. Why did they put 2? The secret there is that they are dividing the non-space with the chip address. So basically, when you send a job on the chain, you send the same job for all the chip on the chain. Okay? So to be sure that the first chip and the second chip are not doing the same hashing, using the same job, each chip will apply its own chip address, but only the first byte, to the most significant byte of the nonce. Okay? So on the 32 bits of the nonce, the most significant byte, so the first 8 bits, will be his own chip address. So if on the hashboard you have 100 chip and you have an increment of 1, the first one will have 1/8 of the non-space to hash. The second one also 1/8. The second one 1/8. But then the next one will have a huge non-space to do it by itself. So they want to divide evenly the non-space using an increment of the chip address so that each chip on the chain get roughly the same non-space to hash. So the first one will be responsible for the nonce value from 0 to 2, and then we are just talking about the most significant bytes from 0 to 2. The second chip will be from 2 to 4. The third chip will be from 4 to 6, and so on and so on. Okay.
Am I correct saying that it's kind of a cheat to avoid overlapping the work from one chip to another?
A cheat or design, or you can call it whatever you want, but that's the way Bitmain is dividing the non-space for all the chip in the hashboard. And by the way, they're doing internally inside the chip. Inside one chip, there is multiple core, 100 of cores, small core, core, not small core, and each core has an internal address also, and they apply this internal address to the next byte, most significant byte of the non-space. So they are sure that inside the chip, no two cores are not hashing the same data, basically.
Yeah, there's like parallel processing going on in these chips of multiple cores,
Exactly.
of hundreds of cores, hashing in parallel.
Yeah.
And that's how you get hundreds of essentially gigahashes per second out of a single chip, right? Because you'd think if it was just working on one hash without any parallel hashing, if it was just working on one hash, then in order to get 500, let's say, gigahashes per second, it would need to run at 500 gigahertz, which is just not how fast these chips can run. They're definitely not running at gigahertz, right? We know that it has a 25 megahertz oscillator clock on it, and we know that the hash frequency is also in megahertz. So you have to think that in order to do hundreds of gigahashes, it's got to be doing them in parallel.
Yeah. And if we look at the last set address command, which is to give the address 250 to the last chip on the chain, okay? So the previous one was 248 and then 250. Then we have a gap because we don't have a power of 2 chip on the board. So the last one will be responsible to hash from 250 to 255. It will have.
And it's not going to, hold on, correct me if I'm wrong here, but it's not going to be able to hash that extra space, right?
Exactly. That's why we have the nonce pattern. The nonce pattern analysis you talked last time on the last stream.
Yeah.
The high end of the non-space is never hashed by the bitmain miner, because of this subdivision into evenly distributed non-space between the chip, and the fact that the chip on the board, the chip count on the board, is not a power of 2.
That's so cool. That's so cool. So, like these chips don't actually have this like onboard buffer of work. So it's up to the control board to send out new work to the chips basically as soon as they're done with their current work. So that means that all of the chips in the chain are going to be done with their specific nonce range, and that last chip still has more to go, but it doesn't matter because you have to send out work to the whole chain. You can't just wait for that last one to finish.
Exact. Especially if you the best way to divide the work is to have maybe a 128 chip on the board and or 256 chip sharp. So then you can divide evenly, and each chip has the same workload. And also each chip internal core should be a power of 2 because they divide the same way but on the lower level. So that's amazing.
But of course, when you're doing the sort of electrical side of a hash board, you need to consider what the core voltage is, what your power supply voltage is, and then how many you want to have in series. Like for instance, I think the XP has 110 chips. It's I think 10 in series, and then it's 11 of those chips in each domain. So that's 110 is not a power of 2. So that's why you have this extra.
Yeah, you have the difficulty to align the number for the software side and then the align for the number for the hardware side. And you never end with a sharp number. Yeah, sure. So then
looking at sorry to butter. Looking at the documentation we had from the registers, I can see there was 3 types of commands and 2 types of responses. So now I seen the types. I guess is what we're seeing in that field in the analyzers, right?
Exactly.
Column.
Right register.
And
yeah.
So from what I was
address.
seeing in the documentation, we had the job command, like command, and chain inactive. So the respond and stuff like that is what is the type 2 is the command.
Exact. Look, if I put the command byte,
Mm.
then you get the 1, which is write register, 63, which is the respond. Then you get the 3, which is the chain inactive, 0, which is chip address, and then we get some write. Yeah, you're true. These are the raw data.
And we should see a nonce response as well somewhere in there, right?
So the nonce response was on the previous when we look at the hashing side. Now we are just in the initialization phase. So the nonce and the job are on the hashing part. So then you can look at here. We got a write register for all chip. So it's a broadcast command to write which register, the core register control, and we give some value, and the value is to write the core 0, to write the core reg write. So there is in-depth protocol. You can dig into the documentation also. But here we have some other writing, register writing. So for some reason I cannot scroll down there. I don't know why. I have some bug. Maybe you also, or maybe I don't know. I can go past a certain point. Anyway, I just want to look at the last command, because if we have a baud rate change, we can expect the last command to be sent to be the information from the control board to the hashboard to say, hey, from now on, I want to change the baud rate to this value. So just look at the last one. And yes, we have a fast UART configuration. You see? So the fast UART control configuration, but my high-level analyzer is not able to extract the correct baud rate from this data, because once again, I didn't have the time and the log at that last year to work on the 62 bitmain chip. So if you put a 66 or 97 chip, then the protocol analyzer will tell you what is the next baud rate value. So you can get the baud rate from here if you're lucky, or if you're using the well-known chip. If not, then you can do what we did before, just trying to make a measurement. It's 3 megahertz also. So, by the way, to have the sharp value, you need to understand that the sharp value is a multiple of 25 megahertz because the PLL is just multiplying the value. So if we want to edit, it's 3, 1, 2, 5. I know them perfectly, but you can just look at the value. Or so we have a 3 megabaud, which is by the way the current or the next block subsidy after the next halving.
Yeah, the coming one is the coming one on
coming
April.
one.
It's dated for 420 so far.
Yeah.
So that baud rate has to be a power of 2 and a multiple of 25 megahertz?
Exactly. So just multiple. That's why also the 115 200 is not a 115 200 sharp. If we look at the data from the hashboard, it's 115 200. Look at the bit size is 8.67, sorry. Okay. But if we look at the response back from the chip, it's not exactly that. 1 bit is there. It's 8.64. Why? Because the response exact baud rate is at 112 200 is 742.
Yes, that's so cool.
Then I get a perfect alignment. But they are able to communicate with this kind of small detail. So now I just did change the baud rate and start again. I can start to see the right register and the right register core value. Let's change. This housekeeping is always the same. And save capture to step 2. Yes, please. Okay. So now what do we want to look? We can look at the frame waveform, or we can just look at the table. It's more concise to understand. On this part of the configuration, okay, the control board is sending a bunch of right register MISC core, okay, the MISC register and the core register, to make some internal setup into the core of the chip. But it's not doing by broadcasting the value to all the chip on the chain. Is addressing one chip at a time. First to the chip 0, then the chip 2, then the chip 4. And this chip is the chip address he was previously allowing to assigning to all the chip in the chain. Okay, and then he gives some clock control and delay control value. Okay, process monitor data. So basically, he's doing the fine tuning of the chip according to the value he has previously read by I2C to the onboard EEPROM of the hashboard. So if we have a related hashboard I2C trace, we can see on that trace that the control board did dump the full EEPROM, and in this EEPROM there are some internal clock delay control and process monitor data that should be fed to the chip for fine tuning. These values are calculated by Bitmain in the factory to do the fine tuning. We were talking earlier about the perfect adjustment to find the sweet spot for the better efficiency of the chip. These values are found in the factory when they do a 1 million chip batch or 10 million, I don't know. They did do the binning, and so by the binning, they affect a different value to each bin. And they assemble the hashboard with only chip from the same bin. So the chip on the hashboard have all a very similar way of response to the frequency and the temperature and the voltage. So basically, and then they wrote into the EEPROM the specific value for the sweet spot, sorry, of the specific hash for this hashboard. And so the control board is in control of that. He read back the value from the EEPROM, which was flashed in production, and send the value to the chip at each boot of the software. So this is the process we are looking now.
So, but there's not like any in the EEPROM, not any hardly written commands for the actual sweet spot. I mean, would be insane if there would be any data like you just load on your software and you can see what would be the best alignment for this specific chip. That's not going to happen. That's always going to be needed to be in control of the software. That's also the reason why we do have this auto tuning functionality with other control board manufacturers, right?
Exactly.
Okay.
So that's why Brain firmware is doing a fine tune. If you use the Brain firmware at high level, there is some fine tuning where you can change this configuration according to the exact hashboard you have, and maybe if the hashboard is old and if it gets hot previously, and so if there is some degradation, then you can continue to fine tune to find the sweet spot of the efficiency. And then Brain firmware is writing that maybe in the hashboard EEPROM, not volatile memory, and then you can extract that and
not in the EEPROM. They're writing a config file. It's in the control board. Brains is, and the firmwares that did write on the EEPROM, a lot of the times they would corrupt the EEPROM, so they can create some issues. It's really better to have a custom firmware that's ignoring the EEPROM altogether.
Yeah. Okay. So you know better than me the high level.
We didn't we sniff the I2C bus last time?
Yeah, we did. We sniffed the power supply.
Oh, that's right. Yeah.
But we didn't get the temperature sensors from the boards. So the only capture we did I2C was the power supply.
That's right. Okay.
So just based on what I showed today, you should be able to use my other high-level analyzer for the I2C protocol and to maybe understand more the I2C communication to the power supply or maybe to the hashboard, to the previous hashboard with the DSP or maybe the new hashboard with no DSP but direct connection to the temperature sensor and to the fan controller. I don't know. There is a lot to do on this way.
I mean, it's definitely like it makes it easier for everybody to understand at least what's going on. Sure, there's a little bit of a fine tuning that you need to do, but just now the amount of work that you put into this so that we don't need to do this is amazing. Really appreciate it here. We need to say this, like it's definitely insane. Sure, there is some fine tuning needed for a couple of things, as you said, a couple of parts, or for example, this A8 sequence that's unknown currently. Someone needs to take a look on it and needs to figure out what actually is going on there. But it's taking us into a place where we can finally understand a little bit more about everything, what's going on, especially between like the control board and the chip itself, because we do know a ton actually, but not everything, and we definitely need to learn a little bit more in order to make the overall vision that we do have, I believe, with the BX happen.
Exactly. And also 80% of the knowledge is already written into the markdown file, into the README from the Scott project. So the documentation I did for the register and everything. So yes, you have to first study carefully this documentation and keep in mind it was written for the 1397. So all the 60 plus chip are not fully the same, but maybe 80% the same. So yeah, we have to be inspired and spend more countless of hours.
So we had a kind of interesting session a while back, but as everyone's aware, we've got the S21 out now, which has a new chip, the 1386, right? And
Is that the 68?
1368.
68, that's right. 1368, new chip. And it's very similar to the 1366, but this is the exciting part. There's a couple extra registers. Have you seen those, Nebula?
Not yet.
Oh man, you got to get into this because there's a couple extra registers. I have my personal thoughts as to what those are, or maybe my personal hopes as to what those are. But yeah, otherwise it's pretty similar to the 1366.
Yeah, so, some work has to be done, and then please join the community Discord and exchange with Scott or me or anyone in the field of reverse engineering the protocol, and we will exchange knowledge with great pleasure, so we can build all together the next generation of BTEX.
Yeah, and I want to insist on how you've been available. And Nebula, the first time I reached out, I told you I've bought my logic analyzer. You right away offered to give a hand and to go through all that stuff. So super grateful to everybody that's contributing, yourself included.
Thank you. That's all the good part of the open source community. We're not there for the money. We're just there for the fame or the fun, or I don't know what you can find in the community, but we have all something to exchange and to make the community, I don't know, happy.
Yeah,
we've made the community very happy with this. I think a lot of this work that Nebula did is instrumental in why the BitAxe firmware works.
Definitely.
That's all for today. Maybe next time we can discuss how to rate the high-level analyzer to make it evolve. So it's basically just a Python script. So I'm suspecting there is a lot of Python-loving programmer over there. I'm not one of them. I don't enjoy really Python, but I do that for the need. We can also discuss the I2C protocol. If you send me the trace you got last time, Jonathan.
Yeah, normally they're on the Discord community. But that said, and now that I know, because to be honest, I didn't know we could split those files and it would save to that save the same. My thoughts is it was local. So now that I know, I will definitely split the files and share them so we avoid that site limit.
So splitting the files is a very good tool, and also keep in mind the initialization part is much more important than the hashing part. Hashing part, if you give us 10 job and 10 response, it's enough. We don't need to have 30 megabytes of job data. Job data is just data. Okay, what we need is the format. So with 10 example, it's enough for the format.
It'd be cool to do is to make an analyzer for the power supply communication. We have a trace of it, and actually, Zach Baumsta, the Loki board maker, he has showed it to me. He has reverse engineered that protocol, and so he has a pretty cool Excel document where he's got it all broken out. But it'd be really cool to make a Saleae. There we go. Jonathan's got his Loki board. You guys sell those, right?
Yeah. So you can get your Loki from us or from Zach if you're in the US, obviously.
I don't know. Maybe we can even get Zach to come on here, but yeah, it'd be cool.
Scott, this Bitmain I2C protocol I did release last time when you did the stream is about that. Is the I2C.
Are you serious? You've already done it?
Yeah, for the APW and the hashboard peak.
Oh my gosh, you've got the APW in there. Oh, dude, you were amazing. Look at that, already done. That was quick. That was like a less than 1 minute turnaround time there.
It was done on my T17 because it's the only hardware I have on my hand, and I didn't have any trace from any one of the S19 generation. So I'm not sure if the protocol will be the same, and for sure it will not be the same, but it will. It may be a different variant. So the basis is there.
Yeah, super useful.
Yeah, I imagine it has changed a little bit. I don't know. Actually, maybe not. It's not super complicated.
We will have to discover by applying the current I2C protocol decoder into the trace you provide, and then we can figure out what is the difference, one bit at a time.
Good material for next stream.
Yeah, there's a pretty cool development on the front. Zach just figured out how to modify the
Yeah.
power supplies, all the S19 power supplies, to operate on 110 volts, which is what we've got over here in North America. So that's pretty big. And I think that there's going to be a lot more development on that front. So perhaps, digging into this APW I2C protocol would be cool, especially if we're coming out with a open source firmware, control board firmware.
Yeah, thinking of the bit cart, I'm just and thinking of that breakthrough with the APW12. Obviously, for next winter season here at Decentral, we'll be aiming to have the whole S19 suite as well. So you can expect to have space heaters based on the S19 and all those nice and useful miner that can be used at home, that are silent, that are adapted to. So I'm thinking the Bitcart and all the breakthroughs we're doing here are going to allow us to make the perfect customization. So we have the perfect home miner, right?
So exciting! This is cool. We'll have to get Nebula to write us an open source miner firmware in Rust, right?
I did the first trial. In the Bitex repository, there is a branch for the embedded ESP32S3 based embassy for asynchronous Rust, no STD, no allocation based miner. I did the driver for the fan controller, the EMC3201. I did the low level controller for the BM1397, the BM chip. I did also work on the ESP32S3 embassy. I did push a pull request to split the UART so we can have two different asynchronous tasks to manage the communication from the chip. There is a lot ongoing there. It can be done.
Yeah, and especially if the firmware is for the Bitcart, which is going to be probably a lot easier to develop for than ESP32 or STM32, because it's a Raspberry Pi, right? It's running
Exactly.
It's running Linux. You're going to have access to all your
so all the allocation and the STD library of the Rust ecosystem. Yeah.
Yeah.
Exactly.
So awesome, guys! It feels like I've been back to school. It's forever. I felt this drain. I'm gonna have to go to sleep. It's very rare that on a Wednesday I feel this drained at this time. But wow, it's really huge stuff. And I'm again super grateful for all the knowledge you're sharing with us and you're sharing with the viewers. I surely hope that some of our viewers are going to be able to join our ranks. We do have a lot of work to do on the BitAx front, and all the projects that are based on it. You can think of the PyAx, the Bitcrane, the Bitcart, and I don't even. I'm missing probably half of the projects right now. The QX that just landed as well. So all of those projects based on that very knowledge that's allowing us to come up with our own products and solutions is really amazing. And I'm again super grateful.
This stuff is moving so fast. It's so exciting.
Crazy.
You got to join the OSMU Discord just to have a chance at keeping track of all these things.
I mean, imagine like you want to have a next high-level analyzer, and NebulaMiner goes, "Here it is. I already done it. I2C, no problem. Here we go."
Actually, I did that last summer because of an idea we got with Scott, and then I didn't release that anywhere because I was waiting for somebody to provide me the trace to be able to test it. And then when I saw you just trying to log the I2C trace on the last stream, I said, okay. So during the stream, I was releasing the protocol analyzer in the marketplace.
Interesting.
Now it's time for the community to use it.
We definitely need to have
remember,
more logs of everything that we do. Like we definitely need to maybe do this more often, or I don't know. Like we need more people that are logging. Definitely.
Yeah.
Yeah. So there is a lot of work to be done, but one bit at a time we can do it all together.
Oh yeah, definitely.
So
Can't
maybe
wait to see more.
one at a time, we can maybe have some closing thoughts and go on with to finish the stream.
I think so too. Yeah.
No
All
problem.
right. So
One
go
you want to
ahead.
go first?
Whatever. So I think I can only like add on what you said. It's feeling like going back to school. I mean, yeah, obviously it's not that long ago for me, but yeah, it definitely is fun to watch all those things like happening and getting educational stuff the whole day long here is definitely something that I do enjoy, especially learning more about ITC and all this asynchronous stuff that's going on. It's like the bare minimum of understanding that you would need to make something high level when you want to create a Bitcoin miner, and that's then what we have seen here is basically the starting point, what we needed to actually create the BitX, and just going through everything. Scott, heads down there. I couldn't do this.
Sure you can. Sure you can. We're all like contributing and working on stuff, and so yeah. I mean, for definitely for anyone listening and everyone here, we talk about lots of crazy high level stuff. We also been working on this for like over a year now. So maybe it sounds like it's easy, but it took a long time to figure it out. It's slow going, and you have to start somewhere. So just jump in, ask questions if you want to know how any of this works, like especially on the OSMU Discord. People are happy to discuss it with you and go off on a tangent.
Just so that you spoke about it, to have this live on stream. When was the first time that you ever thought about you might want to create something like the BitX project?
Oh my gosh, I've been thinking about it for years now. I think. Oh man,
didn't you mention like 2019 or anything like this to me?
Yeah, definitely 2019. I'm trying to think if it was any earlier than that. It was probably around 2019 or maybe a little bit earlier. I wanted to do it, and I bought a bunch of S2 hashboards and started taking them apart. And I read that S5 data sheet that Nebula was talking about earlier, and there was nothing like this before. Like there's plenty of people out there who I'm sure know how it all worked, but no one was saying anything. So it's kind of cool to get this out there, and we're fishing out the people who know how this stuff works, and then we're also figuring it out ourselves and sharing what we know. And it's that exponential progress that is so amazingly exciting. I mean, that's what's cool about this stream, is like we're just talking about this like very obscure project, this very obscure technology and field, and maybe we'll come across a couple people who are interested in it, and who knows what they may contribute. So I guess I just rolled this into my closing thoughts, but I want to say to anyone who's even remotely interested in this, don't hesitate to get involved, jump in, join the Discord, keep watching our stream. All those things. We'd love to have you. We'd love to hear your thoughts.
Just on this question, one clue I want to present you. I don't know if you can see my screen. I'm sharing.
Let me add it. There we go.
Yeah.
Yes.
Look at my NebulaMiner from December 2013.
Oh my goodness. Oh my goodness.
I wanted to do a chain with one ASIC at a time, one PCB, passive dissipation, and you can chain the stuff. And we have one master, which is the control board, connected to the Wi-Fi. So at that time, we don't have any ESP32. It was done by the bridge to Wi-Fi. And then you can, here in this DAT box, I got one of the samples of the Papa ASIC miner, which was one of the first generation of ASICs when the Bitmain did their first generation also. So it was my first design.
That's insane.
Very nice. Very nice.
That was when I was living in China at that time. So I did have access to all this crazy stuff.
Look at those big D sub connectors. That thing is legit.
Yeah, sub 25.
Yes.
25.
That's so cool. How many I feel like the power delivery across that big chain was going to be tough. How long do you think it could go?
Oh, I designed that for up to 8 chips on the chain.
Okay.
But at that time, the power was very low. Maybe it was maybe 5 watts per chip. So it was totally not a big high power.
That was what the chip wanted to run at was 5 watts.
Yeah, but it was also very low hash rate.
Right.
It was in a kilo hash per second. Maybe the NebulaMiner is more powerful than the first ASIC generation.
I mean, I do remember my first butterfly ASIC that I had. They were not that fast.
Look, this was my first hook into my T7. No, it was T17 or the S9K. When I put my Saleae logic 8-bit, I did crimp the header onto the wire, so I was able to man in the middle the stuff.
Yeah, but that has to be a S9K based on the control board, and also because you're fed by 12-volt 6-pin.
Yeah, the S9K I bought on eBay, which was not working. I got one hashboard dead. I was able to sneak the other one. 2022, when I did join Scott on the BTEX project.
Interesting.
So nice.
Some piece of history.
Yeah, that's really neat. I like that idea of crimping on that connector in the middle of the cable. It's a good idea.
All right. So any final thoughts from anybody of you?
Yeah, so, well, that's it essentially. Thanks to everybody, Nebula and Scott. So for the viewers that are looking at what those guys are doing, again, just remember, I don't have any electronics background. I decided just, to put my head into it, put my hands on into it, and eventually, you're able to catch on. So just definitely don't be intimidated. It can look definitely intimidated, and even to this day, there is still some concepts that I get, but they're not fully. Let's say I don't get them fully. So you just put your hands on, and I'm pretty sure that anybody that's giving themselves the trouble and the passion to go through all of that is already making themselves amongst the ranks of the of the mining elites, because there is a few people that understand that stuff, but there's not that many people in the world that understand that stuff.
Yeah, totally. And because we have to learn, but the hard way.
Yeah.
Yeah, we definitely have to. And I do believe, like, with the work that we're doing and with the anticipation that we are doing and giving to the people that are watching this, I hope that we do raise some people's interest to join us and to work with us on this. And maybe someday in the future, we do have a big enough community to actually think about creating a fully open source one. Not only the hardware around the ASIC, but maybe we can go into a fully open source ASIC someday in the future.
Amazing.
Who knows?
That's a very wishful thinking, but
yeah,
knowing for a fact that designing an ASIC is huge difficulties.
Yeah, I mean, if anybody who's watching this does have a couple of millions laying around, just contribute.
It's not about millions. You need to have very high skilled people to the design of the internal ASIC. You can draw. Okay, designing a PCB, I do that for 20 years now. But designing an ASIC is a world of difficulty. You can't imagine the deepness and of the cheat you are going into.
So Block is designing their own 3-nanometer ASIC that they say is going to be open source. So
yeah,
there's hope for the world going forward. And those guys, they are genuinely interested in Bitcoin, and they have, probably thanks to Jack Dorsey, they have deep pockets, but it's kind of cool to see that translate into sort of low time preference interest in Bitcoin. I know they just had like big layoffs the other day, but hopefully they can keep riding through that and maintain that focus on Bitcoin.
Yeah, those layoffs are happening pretty much everywhere anyways right now. In the meantime, until we get our own chips, you have the mining hackers from Open Source Miners United that are going to come up with a lot of solutions based on the existing solutions. So, and I do want to make a small shout out. We just announced at Decentral a partnership with Altair Tech. And so we are also introducing the Bit Chimney and the Earl Laker amongst our product offering. And so these are just some of the ways we're hacking around and making those miners our own miners. So definitely look that up.
That's cool. Altair's good stuff. Decentral's good
Yeah.
stuff. It's a nice
Yeah, thank you.
partnership.
Definitely. All right,
Yeah.
so I think that wraps everything up for today. It was definitely an
Yep.
educational lesson for today. It was definitely something that I did enjoy. It's sometimes a little bit rough, but definitely something new for me today. So that's
For sure.
thank you, a big thank you from my end
Yeah.
here to you, Nebula. You're really a legend to me. Knowing all this stuff, this is just blowing my mind.
Yeah, the deep sea is difficult to see, but when you are swimming, then you can learn a lot of stuff.
There you go.
All right. I think it's a good end to the stream. If anybody else want to add anything else, otherwise, I'd say goodbye to all the viewers here, and that's
Tune in
it.
next time.
Peace.
See you the next